equations of planes. We're going to start with very, very simple equations. In 3D, if we have x equals a, or separate equation y equals b, or z equals c. Now these are three different planes, different equations. Remember what we mean by those equations. So what we mean by x equals a is the set of all the x, y, z's in R cubed such that x equals a. So that means that y and z are free to be whatever they want to be. So that is the equation of one plane. The second equation, y equals b, means all the x, y, z's in R cubed in the space, in the three-dimensional space, such that y is equal to b. So let's draw a little arrow indicating that's that. And then z equals c means all the x, y, z points in space, three-dimensional space, such that z is equal to c. So that's what we mean by that. So it is not just one point, it is a whole bunch of points with those characteristics. Remember that when we draw the three-dimensional space, the plane containing the x-axis, so this is the x-axis, and the y-axis is called the xy plane. The plane containing the x-axis and the z-axis is called the xz plane. The plane containing the y-axis and the z-axis is named the yz plane. So x equals a is cylinder, a vertical plane that goes this way. We cannot draw the whole plane. We draw part of it. This did not line up correctly, but that's the plane. So it is, this plane represents x equals a, and it goes through the point A. And then we have y equals b would be a plane going this way. So it goes to the point y equals b. And then z equals c would be a plane that is horizontal. So it goes through the c. So those are three different planes. This would be x equals a. That one is y equals b plane. And this is z equals c plane. And they would intersect at a point somewhere, with coordinates A, B, C, somewhere in there. But I don't want to necessarily show right now the intersection. I just want to show the planes. So again, if you see simple equations such as x equals 5, well, that means 5 units up above horizontal plane. I'm sorry, I meant z equals 5. If you see z equals 5, that means 5 units up above the origin, a horizontal plane. If you see y equals 5, that means 5 units to the right, a vertical plane. A vertical plane. If you see x equals 5, that is a vertical plane, but this time it is facing us. We can see most of the area. This one we see a profile of the plane. Yep. Okay, so we have those cases, those scenarios. If we have only one variable equaling a constant, those are the kinds of planes we have. If we have two variables and only two variables, so say you have x plus y equals 5, let's start with an actual number, then this plane is a cylinder. And what we mean by this is the set of all the points x, y, and z that belong to the three-dimensional space, such that x plus y is equal to 5, while z can be anything. So there's no restriction on the z. So this equation as a three-dimensional plane would be, okay, so there's the x-axis, y-axis, z-axis, and the plane, if you draw this actual line, x plus y equals 5, on the xy plane, we would have this line, there we go, where this would be 5 and this is 5, and then the plane in 3 dimensions would be, let's go up, diagonal, there we go. So that is the plane x plus y equals 5, where this is 5, and so is this number 5. If we have x plus z equals 5, that's a different plane. Let's see. First, we can draw the line x plus z equals 5 on the xz plane. So that would look like this. And then the y value could be anything, so we can extend it in any length. Then copy this. So this plane, this would look like a ramp to us. This is a vertical wall, while this is a ramp. So if you were on the xy plane and then you bump into this, you would be going up on the ramp. But remember, this plane keeps going down through the xy plane, and it extends in every direction straight. So it keeps going up and down and to the sides here. So we cannot draw the whole plane because the whole plane has no finite length. Just like this one doesn't have a finite length. This is just the first octant, but not even the whole, because this keeps going up. We don't have the whole plane because this goes up and down and to the sides. So there's more to it than just what we are drawing. This is just a short representation of the plane, and so is this one. Oftentimes that is enough for us to know what's going on. And then if we have y plus z equals 5, then we have this line to start with, and then we can extend the plane in this direction because x is free to be whatever it wants to be. Yep. So we have 3 kinds of planes. Vertical one, a ramp. If you come from the positive x-axis, the ramp goes up. And if you come from the positive y-axis, in this case, the ramp goes up as you encounter this plane. So those are the 3 basic cases. Of course, if you have 2y plus z, for example, equals 5, then you have to change these numbers. Right now, this is 5 and this is 5. They're not proportionally correct in my picture, but assuming that they were proportionally correct, this would be a 45-degree angle plane. However, if you change the coefficients of y and z, then that changes the slope of the plane, and so that's here. But if you have 2 variables, then we have that. If we have 3 variables, yeah, let me give you the general case. So we had the case of 1 variable in the equation, and that's it, 2 variables. If we have 3 variables, 3 variables. Say you have ax plus by plus cz equals d. So those are the variables x, y, z, and the corresponding coefficients a, b, c, and then d. We're going to assume d is not equal to 0. We're going to assume also that a, b, c, when we multiply together, we don't get 0, so all of them are non-zero. And we're going to assume that A, B, C, this is not a vector, but the three elements are all positive. I guess this was sufficient. If we wrote this down, then we didn't have to write this, because if they're all positive, then the product will not be 0 anyway. So this plane will go through the x-axis, the y-axis, and the z-axis. Under those conditions, we're going to have a plane that looks like this. Well, again, this is not the whole plane. The plane actually extends in every direction, up, down, in every direction. This is just one portion of the plane in the first octant. So the intersection here would be D divided by A. So that intersects at D over A comma 0, 0. This intersects at D divided by B, 0, D divided by B. And then we intersect the z-axis at 0, 0, D divided by C. All right. I apologize for that noise. It's the telephone. To any plane, we have a vector. So let's draw a general plane. Actually, we have a multiple of vectors that are called normal vectors. So any vector that is perpendicular to the plane is called a normal vector to the plane. So this guy is a normal vector to the plane. And there are many normal vectors. You can have another one there, shorter. It doesn't matter the length, what the length of the vector is. It can be short, long. It can actually go in the opposite direction. And that is another normal. So all of those are normal vectors to the plane. What is important about a normal vector is its direction. Its length is not important. So if we multiply a normal vector by any non-zero constant, we end up with another normal vector to the same plane. Let's write that down. That is important. So if we multiply a normal vector to a plane by any non-zero constant or scalar, then the resulting vector is also normal to the plane. Okay. It turns out that if you have the equation ax plus b y plus cz equal to d, then, so this is a fact, the vector a, b, c with coordinates a, b, and c is perpendicular to this plane. Let's write it down as a fact. Okay, so the vector a, b, c is normal to the plane ax plus by plus cz equals d. I guess I could have said just the above plane or the plane shown above. Let's take the time to prove this very quickly. So if you have any plane, it doesn't have to be horizontal. Sometimes I tend to draw horizontal planes only, so I have to think about that when I'm drawing planes. Practice drawing things, by the way. So here's the vector ABC. Well, we don't know that it is necessarily perpendicular. We claim it is. A, B, C to the plane. Let's pretend this point here is at the base of the vector. So we have, and let's label this point as x naught, y naught, z naught. And then we have a point here, a generic point, x comma y, z rather, x comma y comma z. So we want to show that the vector ABC is perpendicular to this vector from xyz, a generic point on the plane, actually, that the vector from this point to this point, and this point is a generic point on the plane, this vector is perpendicular to ABC. Yeah. Yeah, because the origin is somewhere else, not necessarily right on the plane. So if we don't want to show that XYZ is perpendicular to ABC, we want to show that vectors on the plane, which are obtained by subtracting two points on the same plane, that those vectors are perpendicular to this one. Yeah. So the way to know how two vectors are perpendicular, or one way to know if two vectors are perpendicular, is by finding their dot product. So let's find the dot product of this vector and that vector. So we do A, B, C dotted with this vector, which is x minus x naught, y minus y naught, z minus z naught. Okay. This is a floating vector, as I think of this. It can be misleading. We're not talking about the vector from here to here. We're talking about this, and that is why the direction is important. A vector with that direction, regardless of where it is anchored at. So whether it's at the origin or here, those two are meant to be parallel. So when I put down ABC, I don't mean the point ABC, we mean ABC as coming from here to there, we go ABC. Yeah, that is a little confusing. This is a direction, and the vector here, which is another direction, is taken from here to here, not from the origin to there. So anyhow, we multiply, we apply distributive properties. So the A multiplies with the x minus x naught, which in turn means that we multiply the A with the x and then the A with the x naught. So we end up with AX minus AX naught plus, remember the dot product is a scalar, and we find the scalar by multiplying corresponding terms and then adding those products. So this is one product. A second product will be y, by rather, minus by naught plus cz minus cz naught. Now, this is a real number made up by this number, this product, minus this product, plus this product, minus this product, plus this product, minus that product. We can rearrange them, reassociate them. So this is the same as AX plus BY plus CZ. And then we're going to reassociate the other ones, factoring out the minus. So this is minus, minus, and minus. AX naught plus, because we're factoring the minus, BY naught plus CZ naught. Now, X, Y, and Z is a generic point on the plane, and consequently, it satisfies this equation. So when we multiply with the X, Y, and Z's with A, B, and C correspondingly, we will end up with D, because again, the point satisfies this equation. So this product down here, rather this sum of products is equal to D. This point also is on the plane, so that is also equal to D. D minus D is equal to 0. And consequently, those two vectors, this shows that those two vectors are indeed perpendicular. Yep. So if you have an equation AX plus BY plus CZ equal to D, automatically A, B, and C is in the direction of the normal vector, or it is a normal vector of the plane. Let's do an example of finding a plane. So let's call this example 1. Okay, we're going to find the plane passing through the points 1, 2, 3, 3, 1, 0, 7, -3, -2. You can use any non-linear, rather non-collinear points, any 3 non-collinear points, and that will give you a plane. All right, so we got 3 points. We can label this as A, B, and C. So we have 3 points, A, B, and C in space. There's the origin somewhere. And we want the plane that contains those 3 points. There's only one plane that contains those 3. So one way to go about it is to find this vector and this vector. Those 2 vectors are on the plane, those directions. We can form the cross product to find a normal vector. So this vector is going to be perpendicular to both. And then once we have the normal vector, that is equivalent to obtaining the slope. When we are finding the slope of a line, the first thing that we typically do is find the slope of the line. So similarly, the coefficients A, B, and C are the slope in quotation marks, the slope of the plane rather. They give us the direction of the plane. All right, so anchor those 2 points using one of the points, the other point. So there's 3 points. We can anchor 2 points using one of the points as the anchor. So in other words, let's shift everything to the origin. Well, not everything, so that one of the points becomes the origin. And I'm going to choose A to do that because I already drew the picture. We could have chosen B or C. So subtract B minus A Let me do the computations down here. I think this is enough space. So b minus a will be the vector 3 minus 1, 2, 1 minus 2, negative 1, 0 minus 3, negative 2. Again, I'm going to repeat 3 minus 1 is 2, 1 minus 2, negative 1, 0 minus 3, negative 3. Good thing I checked. That's 0 minus 3 is negative 3. C minus A, 7 minus 1 is 6, negative 3 minus 2 is negative 5, negative 2 minus 3 is negative 5 again. All right, so those are the two vectors, b minus a and c minus a. Cross them. So b minus a crossed with c minus a. Let's see, the first coordinate of the cross product is going to be 5 minus 15, negative 10, comma. Then we multiply those two, negative 18 plus 10, negative 8. And then the cross product here is negative 10 plus 6, negative 4. Now, what we care about this vector is its direction. We don't care about its size or whether it's going one way versus the opposite way. See, we can factor negative 2 and have simpler numbers, 5, 4, 2. If we factor out negative and 2, we end up with this. And this is a direction that we want to keep. Again, multiplying a direction with any non-zero number or dividing by any non-zero number. In this case, we would be dividing by negative 2 to get rid of this negative 2, provides a vector with the same direction. I was going to say the direction is not quite right because it is actually going to go in the opposite direction, but in the same slope, in quotation marks, slope. And that's what we want. So in order to obtain the equation, we have the coefficients 5x plus 4y plus 2z equals a constant. We don't know what the constant is. The way to figure out the constant, I'm going to put a question mark, is by plugging any of those 3 points in here, and that will give us the correct constant. So if we put 1, 2, 3 here for x, y, and z, we will end up with the correct constant. So 5 times 1 plus 4 times 2 plus 2 times 3 will give us 5 plus 8, 13, plus 6, 19. It's a good idea to double check that it works for all of the other points, because if I made a mistake in any of these steps, we did a couple subtractions, we did the cross product, which is not simple, and then we factored. There's many places where I could have made a mistake. So in order to check that the answer is going to be correct, it is a good idea to go back and plug in all of the 3 points to see if we end up with the same constant. If we plug in 3, 1, 0 with the same coefficients, 5 times 3 plus 4 times 1 plus 2 times 0, 15 plus 4, 19. So it checks with 2 of the points, might just as well check with the last one. 5 times 7 plus 4 times negative 3 plus 2 times negative 2, 2 times negative 2. Let's see, 35 minus 12, 23, minus 4, 19. So the equation 5x plus 4y plus 2z equals 19 checks with all of the points. checks with the first one, checks with the second one, checks with the third point. And consequently, this is the equation of the plane that goes through A, B, and C. 1, 2, 3, 3, 1, 0, 7, negative 3, negative 2. Practice how to do this. It is very crucial. Oh, one thing I would do if I were you is anchor your system, your 3 points, to another point. So instead of using B minus A and C minus A, use, for instance, A minus B and C minus B. So subtract this point from those two, cross them, you should end up with a direction that is slope. I'm going to say slope in quotation marks. Slope. The reason why I am differentiating slope from direction is because a direction in physics oftentimes has a one-way, and a slope has two ways. You can go either way in a slope, although somebody could say, wait a minute, if we go in the positive direction, there's only one way, and that is true. Anyway, practice anchoring your system at B, anchoring your system at C. And after simplifying, you may end up with extra numbers. For instance, you may end up with, in fact, that could have happened easily here. Had I kept the negative 10, negative 8, negative 4, we would end up with negative 10, negative 8, negative 4, and we would end up with negative 76, if I did the computation correctly in my head. But then we can simplify by dividing by negative 2 to keep numbers as simple as possible, which we should always attempt to do. Let's talk about the distance between a plane and a point. It is handy to figure out this distance. So pretend you have a generic plane with equation ax plus by plus cz equal d. We already know that the perpendicular vector, the normal vector to this one, a normal vector, because there are many, a normal vector to this plane would be a, b, c, the coefficients of the equation. And let's assume P is here. P would be a point off the plane, capital P, with coordinates L, M, N. And we want to find this distance from P to the plane. Yep. One way to go about it is to take any point Q on the plane with coordinates X, Y, and Z, satisfying this equation. Okay, finding this vector and projecting it onto this normal vector. If we find the component, that will give us the distance, because this point we want this point to project into the normal vector, and by finding this component, the component of this generic vector into this vector, that will give us the distance. Yep. Yep. Remember, one way to find to think of components is thinking, okay, if you want to go in this direction and then go in a normal way, go 90 degrees to get to this point, the way we go about doing that is to find the component, which we already covered in the dot product section. So what we want is this distance from here to here. So this is, well, let's find the component first. So we want this component first. So the component, scalar component of the vector from Q to P, the vector from Q to P onto ABC. That's what we want to find. And from the dot product section, we learned that this is the dot product ABC dotted with QP and dividing by the magnitude of ABC. ABC, this is a vector, and we're going to find its magnitude. All right, so that is equal to ABC. The vector from Q to P is P minus Q, or L minus X, comma, M minus Y, comma, and N minus Z. All right, that is equal to, oh, I missed to divide by the magnitude, which would be the square root of A squared plus B squared plus C squared. So that is equal to, again, we're going to distribute, this is the dot product. So we're going to distribute A into L minus X, AL minus AX, plus B, M minus BY, plus CN minus CZ. We're going to divide all of that by the square root of X, A squared, plus B squared plus C squared. And then let's group so that the ones that we're not subtracting are going to be together, AL plus BM plus CN. And then we're going to subtract AX plus BY plus CZ over the square root of A squared plus B squared plus C squared. I'm going to continue on the next sheet. So again, we're finding the component of QP onto ABC. And from the previous page, we have, I'm going to continue down here, AL plus BM plus CN minus, now XYZ is some generic point in this plane. And consequently, if you plug in X, Y, and Z into this equation, you're going to end up with D. So this part is equal to D. So we can subtract D. And then we still divide by the square root of A squared plus B squared plus C squared. Now, that is the component of the projection of this vector onto this one. The problem is we don't know whether this vector is pointing in the same direction as the point P or on the opposite direction. It could go one way or the other. We don't know which way it is. So the component could be positive or negative. We don't know in advance what it is. So we use, for the distance, D for distance would be the absolute value of this difference, AL plus BM plus CN. Subtract D, close the absolute value, and then divide by a squared plus b squared plus c squared. So that is the formula for the distance between, so let me repeat, distance between the plane ax plus by plus cz equals d, and the point LMN. Let's look at an example. Remember our plane, the plane we found. Yeah. So let's do an example 2. So let me give you some background. We found a plane with equation 5x plus 4y plus 2z equals 19. And this plane goes through the points, or contains the points 1, 2, 3, 3, 1, 0, 7, negative 3, negative 2. We figured this out already. This was example number 1. The plane that contains these 3 points happens to be this one. All right. Let's change this point a little bit. Let's move it up, whatever it is. It's not too hard to figure out where it is. It's 1 unit, 2 units, 3 units. Let's shift it up a little bit. So we're going to change this point. We're going to have a new point with coordinates 1, 2, 4. So we're just shifting the point up 1 unit. The question is, so here's the question. What is the distance between the plane 5x plus 4y plus 2z equals 19 and the point 1, 2, 4, question mark. Now, we would be naive to think, although we may be thinking at first, but after thinking about this, we realize that it is naive to think that the distance is 1 unit, because all we did is move the point 1 unit up. So this is sort of what's going on. Pretend that is a profile of the plane. We had a point. You know, we're looking at the plane from its side. And then if we shift this point up 1 unit, let me do this, up by 1 unit, which is what we did. This point used to be, so this point has coordinates 1, 2, 3. Now we moved it up to 1, 2, 4. The question is, what is the distance of this point to the plane? Well, it would be naive to think that it is 1. It is not a 1 because the distance is always taken perpendicular to the plane. So if we put this as a horizontal, what we really want is this distance, not this distance. This distance is 1, but what we really want to know is how far off. What is the gap, the space, the smallest space between the point and the plane, which would be this much, this distance. So according to the formula we did, the distance is the absolute value. Okay, so essentially it boils down to this. Plug in this point into the left side of the equation when written that way. So 5 times 1 plus 4 times 2 plus 2 times 4. Whoops, I want to be consistent, 2 times 4. Subtract 19 minus 19 and divide by the whole thing by the square root of 5 squared plus 4 squared plus 2 squared. So the distance is equal to absolute value 5 plus 8, 13, plus 8 again. That's a 2, sorry for the smush. 5 plus 8 is 13, plus 8 is 21. 21 minus 19 over the square root of 25, and 16 is 41, and 4 is 45. There's no need to put the absolute value in this case, but we did not know that in advance. It turns out that the normal vector and the point are both above the plane. So 2. And then we simplify the square root of 45. That is 9 times 5, so 3 square root of 5. And that is exactly the distance between the point and the plane. No more, no less. I believe I did this earlier. Yes, in my calculator, if I'm not mistaken, this is approximately 0.3 units. So what that means, now that I see this number, is that this distance should be a third of this distance, which was 1. So that means that the plane is actually more inclined. It is more, it has a steeper slope with respect to the horizontal, because when we move 1 unit, one unit up, the corresponding distance here is going to be only a third of that. Actually, it's probably even more steep than that. The plane is quite steep. Yeah, 0.3 is small compared to a 1 unit. That is interesting. Now, I wonder if you move this point up 1 unit, so 3, 1, 1, is the distance of that new point, 3, 1, 1, going to be the same as here? The distance to from this point after we move it up 1 unit, is it going to be the same as that one? That's a good question. I think. What if we move this up 1 unit, 7, negative 3, negative 2, and then we move it to 7, negative 3, negative 1? What is the distance between the new point after we shift it and the plane? Is it going to be the same? Yeah, and then the other question is that I'm thinking of, what if we move this point to the right, rather forward towards us? You know, if we change that 1 into a 2, how is that gonna, how much are we gonna move it off from the plane? Or what is the distance from shifting this towards us by 1 unit, or move it to the right? If we change that into a 3, how is it gonna affect, how is the distance gonna be affected? By the way, the distance from this point to the plane itself should be 0, and we do obtain 0 because when you plug these coordinates into this equation, we're going to end up with 19. 19 minus 19 is 0, so we're going to end up with an answer of 0, as we're supposed to obtain. Okay, that's the end of the equation of the plane.